Good afternoon or good morning, everybody. My name is Hal Finkel. I am a program manager at the U.S. Department of Energy, Advanced Scientific Computing Research Program in the Office of Science. And I'd like to thank all of you for joining our panel today. We have a very exciting panel on how we're going to program future systems with a number of distinguished panelists. And I'm going to let them introduce themselves in just a minute. And then we will go through our pre-selected questions. But preferably, if you have questions that you would like to ask the panel, I encourage you to put them into the Q&A feature in Slido through Hub. We should be able to see them there. And with that, I think we'll get started. So I've asked each of the panelists to, they'll introduce themselves and then take a few minutes to share any kind of initial position or opinion that they would like to put forward. And then we'll start with the Q&A. Kathy, would you like to go first?
I'm Kathy Yellick, and I'm a professor in electrical engineering and computer sciences at UC Berkeley. And I will be starting as the Vice Chancellor for Research there in January. And I'm also a senior faculty scientist at Lawrence Berkeley National Lab. And I guess in terms of my initial thoughts on programming systems for HPC and scientific computing in general, I think we should think about how people are programming it at a much higher level of abstraction than we're used to. I think if you look at machine learning and the packages that people have built for machine learning, that they've really shown that you can, with a lot of work in terms of how you implement some of those underlying algorithms, get very good performance out of those, and that it opens up the HPC type of access to a much broader community of people if they can program at the level of something like TensorFlow. And I'd like people to also think a little bit about systems like Julia and Jupyter notebooks as really the interface to the computers, rather than thinking about programming in languages based on, say, C, C++, or Fortran. So that's really, I guess I'm going to be advocating for much higher levels of abstraction, which is not to say that some of us won't still be programming at a much lower level and trying to build the systems that will help each of these higher level abstractions go faster.
Okay, great. Thank you, Kathy. Saman?
Hi, everybody. My name is Saman Namarasinghe. I'm a faculty member in EECS at MIT. And I have been working on compilers and basically trying to make programs run fast. And when I was young and naive, I thought I can take general purpose programs written in C and Fortran and make them run really fast. And as I have aged, I have made, as Kathy said, gone more and more higher up in the stack, trying to use domain-specific languages. Actually, if you think about domain-specific languages, it's not too much of a stretch. So even if you say you are a C programmer, or a Fortran programmer, or Python programmer, nobody writes loops and arrays and low-level things in these languages. We all use libraries. So all the users of these systems are based on libraries. And so that means we are already programming at a higher level abstraction with one caveat. These libraries don't have understanding how the entire thing is connected together. So when you call a library function, it's a standalone thing. It will do what's asked and return. What a domain-specific language or domain-specific compiler does is it can figure out the control flow between these library calls, understand how these things get stretched together, and then use that to give good performance. This is especially important in now and the future because memory systems and data movement is becoming a really important issue. So to understand the big picture, how data moves within the program is going to be very critical to get good performance. So having that kind of abstraction is necessary. So to give you an example, if you look at a language that we developed some time ago called Halide, this language is now used for a lot of image processing and computation like that. And very popular, like if you use your iPhone or Android phone, all the camera pipelines are written in Halide. if you write in Halide, it looks almost like you are writing a library calls or a little bit of overloaded functions in C++. That's what this Halide looks like. But at the end of writing the program, instead of saying, running the program, it says, okay, collect all the things you write, the program in here, now compile, now optimize, and now give me optimal thing, which I give the data and I can run. And by doing that, for the program, it looks very much like using a library, but you can get orders of magnitude better performance. So I think as we move forward, what I would like to see is have lot of the library looking domain specific languages that would be a very simple switch between a programmer who uses libraries into these domain specific languages. But because you have this ability to understand what you are doing overall and understand domain knowledge to give you good performance. So that's a hope. And in few domains, we have done that. And we hope we can do that in more domains. So let me stop there.
Okay, thanks, Sam. Torsten?
Okay, I'll some slides if I may. So, are we seeing your slides? Not yet. Okay, perfect. Okay, thank you very much. My name is Torsten Hassler. I'm from Ubiquitous. Okay, I am muted now. Does that work?
Yeah, that sounds better.
Yes. Okay, perfect. Thank you. I'm hoping the Zoom channel still hears me, but yeah, my name is Torsten Hassler. I'm a professor at ETH Zurich. I'm physically here, as you can tell. And my point is to say data movement is all you need. And literally, you don't worry about anything else. So let's get into this and see what the story is. If you could actually imagine one workload where you would say that is not data movement limited, that is actually really just compute limited, you would probably get to matrix multiplication. This is something that we've been doing for decades in LinPack. And now I can tell you that, well, transformers, modern deep neural networks, are very much matrix multiplication dominated. So these architectures like BERT and GPT-3 and GPT whatever, all these encoder-decoder based architectures are really matrix multiplication with a little bit of softmax on top of it of various shapes, and I can go more into detail, but let me not get into detail. One fact is that these are extremely important. So in some sense, many companies are spending tens of millions of dollars to train these models, and these are real HPC problems. They're the largest models people have trained, so very much like we care about. And what we did is we actually analyzed the workload a little bit more in detail, and this analysis led to the fact that we found that what is obvious is that the 99.8% of the workload is, 99.8% of the floating point operations in this workload are actually tensor contractions. So these tensor contractions are all expressed as matrix multiplication. So this is wonderful, isn't it? So 99.8% of this workload is matrix multiplication. But then if you actually look at the remaining 0.2% of multiplication, of operations in this workload, it's 0.2%. Turns out that those are actually taking about 40% of the runtime because these tensor contractions have been super highly optimized over the years. So they run on tensor cores, and now you apply Amdahl's law, and suddenly you are somehow in a problem because now everything else dominates, and this is data movement. So we did some optimizations that I don't want to go into detail that just show that you can actually speed this up quite significantly, and you can save millions of dollars by just looking at data movement. This is just one particular example. You can look at the paper here. In fact, you can look at a YouTube video of this whole thing by my wonderful student, Andre, or you can look at the paper if you want, so there are all kinds of references here. But I will not go into detail. But my problem is now that 10 years ago, if we go back to the exascale, the beginning of exascale, where Jean Schalf and colleagues wrote this wonderful paper, Exascale Computing Technology Challenges, and they pointed out in the abstract, in particular, they will need to manage locality to achieve performance. So somehow and this was 10 years ago, and somehow we are still counting flops today. So how did that happen? So how can we still count flops and not actually count data movement? How can we even do the undergrad education that we do? So how can we teach computational complexity in terms of operation counts and not in terms of data movement? So this is something that we really need to change somehow. Unfortunately, I/O complexity is extremely hard, so it's much harder than counting operations. So we need to figure out how to do this. And there's one problem with this that I just want to mention briefly here, and we can discuss this later if we want. What does high bandwidth even mean? If I'm achieving high bandwidth on a system, does that mean that I'm using that system efficiently? And the answer is, of course, no. Otherwise, I wouldn't be asking that question. And so we introduced a metric for this, which we call memory use efficiency, which is somehow an I/O complexity related metric. It's like flops or peak flops, but it's bandwidth centric. The problem with bandwidth is that it's extremely easy to use your memory subsystem very inefficiently if you don't do things like tiling for matrix multiplication, for example. You use your memory subsystem extremely inefficiently, and you don't even know because you may be getting 100% or 98% of your memory bandwidth. It's just that you're not using that bandwidth efficiently. So what we did in this memory use efficiency, we basically looked at what is the lower bound of operations we need. So for matrix multiplication, we can compute this efficiently. Then we look at what is the algorithm we are running actually consuming. So we get some kind of I/O efficiency factor. And the second factor is trivial. I mean, this I/O efficiency factor is quite hard to figure out, actually, because I/O lower bounds are not easy to get, as many of you know. But the second factor is just the measured bandwidth divided by the peak bandwidth, so this is the obvious one, this like the peak flops. But you need the first factor, right? So that's something we may want to discuss. And so just to finish my point here, it does work in practice, and it does work in practice also in HPC. So, for example, looking at my esteemed colleague Alex Eichen, who gave a wonderful keynote at the Charm++ workshop, which you also find on YouTube. By the way, one of the best things that happened in the pandemic is that all these talks are on YouTube, so you can just watch all the famous people. You don't have to travel anymore. So I opened up YouTube, watched Alex talk, and what I found surprising in his talk was that he actually cites our work, which we published in SC21, as the best matrix multiplication. And you know what? The whole optimization, distributed matrix multiplication on CPUs, the whole optimization we did there was pure data movement. We only looked at the moved data for matrix multiplication. And you can actually continue this line of work. On Thursday at 10:30, one of my students will physically here be speaking about how to do that on LU and Cholesky, basically apply the same idea, find a lower bound, lower I/O complexity bound, find a schedule, or sometimes people call it an algorithm to do this, and then solve the problem faster than anybody has solved it before. And we would rule the top 500 list if we would just be allowed to get away with our pivoting strategy, which we are not because the rules forbid us to do so. So now the question is, if there was just a tool to do this, data movement analysis, wouldn't that be great? In fact, we are developing such a tool, so this is just a plug here for what we are doing, and we can debate this later. So we actually have a framework where we can model data movement in applications, and you can just hover over those things here, as you see in this GIF. And you see parametric expressions for how many flops are happening. This is a matrix multiplication, by the way, and how much data is moved. And for this trivial example, it's obvious. For more complicated examples, it gets quite interesting. And then you could also look at various ways to transform these codes into different new representations, which is then built into the framework. So it's kind of an automatic optimization and data-centric transformation framework. So with that, I would like to stop my presentation and hand the helm on. Thank you.
All right, Torsten, thank you very much. Justin?
Yeah, I actually have become wildly inspired by Torsten, and I'm hoping that I can now share. Can you see my screen?
Yes.
Yep, it's here.
Okay, wonderful. Yeah, so Torsten, thanks for sort of inspiring me. I actually just presented this lecture, Kathy, at Berkeley in Alvin Chung's class last week. So maybe I can just introduce myself and give sort of my high-level view. So I'm a principal AI scientist at Intel Labs. I'm also the director and founder of the Machine Programming Research Group at Intel. And I hold an adjunct faculty position at University of Pennsylvania. And lastly, I'm the steering committee chair of the ACM SIGPlan Machine Programming Symposium, MAPS, formerly known as MAPL. And back in 2018, we published this paper, actually jointly with Saman and some others, on the 3 pillars of machine programming. Machine programming is principally this idea that we are going to try to automate the development of software, and a byproduct of that is the automation of the development of hardware, given that much of hardware is developed through software. And the 3 pillars are intention, invention, and adaptation. Intention is principally concerned with trying to identify novel ways or improve the existing ways for programmers to specify their ideas to the machine. So going back to, I think, both Kathy and Saman's comments about higher order abstractions and DSLs, in fact, I fully agree with this. And I think that as we move forward, I suspect that in order for us to get outstanding performance, we really need to have this separation of intention from invention and adaptation, which I'll show in just a second here. Once the intention is understood by the machine, then we can start to invent the algorithms and data structures that are necessary to fulfill that intention. And predominantly, from my view, we want this at a higher order representation. So one possible way is through something like verified lifting, through a lambda calculus that, like what Alvin Chung is doing. Once that's done, then we can take that higher order representation and then adapt it to specific hardware and software ecosystems. And one of the benefits of this approach, as I see it, is it becomes very portable, and it allows it to evolve as programming languages evolve, as hardware evolves, as these various ecosystems evolve. Because the higher order program that you capture in the invention pillar doesn't actually contain any of the system level details. Instead, it's just a higher order representation of the intention. And intention is also concerned with things like lifting the semantic meaning out of existing software and then being able to sort of repurpose it for optimization, additional correctness, security, things of that nature. And then the fourth hidden pillar is that data is predominantly everywhere. But to see sort of a concrete example of this, going back to Saman's point, if you look at Adobe Photoshop version 21, you actually will see a combination of verified lifting and Halide together. And the way that this works is they lift out the semantic meaning from existing C, C++ code into that higher order lambda calculus that I was just mentioning. Once that's done, they do semantic verification that the semantics remain the same from the original program to the higher order lambda calculus. After that's been done, they can lower it down to Halide. And the beauty of Halide, as Saman was saying, is it tends to generally just capture intention. It separates out invention and adaptation. Essentially, there are two, when JRK was originally building this, there were two programmers. The algorithm programmer, that's the intentional programmer, and the lower level computer engineer, computer ninja, software ninja programmer. What we find though, as we've evolved Halide, is that we can elide away this ninja programmer to some degree and use the techniques that I think Kathy and Saman were hinting at on using machine learning and other ways to find more optimal solutions, as the machines tend to have the freedom to explore more possible optimizations than humans can. But the core idea for this to work is intentionality has to be separated out from invention adaptation. For example, if you have a lower level programming language like C and you add an if-def x86, now you want to port that to some other hardware architecture. Well, now that you've bound some of the adaptation ideas into that program, the machine may have a more difficult time reasoning about what you're actually captured is inside of that x86. Is that semantic level detail or is that system specific? And if it is semantic level detail, how do we lift it out from a very specific vectorization or cache alignment type of thing? Whereas if it were represented in a higher order semantic level, like this lambda calculus or these higher order things that like Kathy was mentioning, TensorFlow and PyTorch, it frees up the computational exploration for the machine under the hood to do these things of orders of magnitude performance improvement. And you don't have to take my word for it. You can just read this fantastic paper written by Maz Ahmad and colleagues, automatically translating image processing libraries to Halide. I'm not a co-author on this, so I'm not bragging about my work here, but this is what they actually saw when they applied verified lifting and Halide to existing Photoshop code. They did a transpilation of those original functions to Halide, and then ran Halide's stochastic optimizer using something like a tree convolution search. And they were able to improve the performance by 3.3x on a geometric mean, which is approximately like 230% performance improvement, while simultaneously only taking 200 total hours to do the transpilation, which likely means that not only do we get superhuman performance, we get it at orders of magnitude faster than we would if we would have done this through manual labor. So at this point, I think maybe I'll just stop talking. And now I think maybe I've shared my high-level view on how I see things.
Okay, great. Dustin, thank you. Maya, last but not least.
Okay, well, thank you. There's hardly anything left to say at this point. We've had so many different viewpoints and very insightful comments, but I did prepare a couple of slides, and so I will, let me see if I can share them and go through them quickly, because as I say at this point, we probably know everything we need to know.
That's great. Maya, also introduce yourself, please.
Sure. So I am Maya Gokhale. I'm a researcher at the Lawrence Livermore National Laboratory. I've been there several years. I was at Los Alamos before that, and I'm interested broadly. I'm so glad you invited me, because I'm very interested in programming models. I've designed and implemented a few parallel programming languages through my career, and have had some experience with that, and so I thought I would kind of from that viewpoint just give a little overview of what I have learned and the insights that I have. Okay, I'm going to talk a little bit about programming model challenges in the landscape of ubiquitous heterogeneity. This is what we're facing these. That, you know what, I had recorded that, but it's a little long. It's 7 minutes, so I don't know if you want me to skip through it quickly and not go through the whole talk. Hal, what do you think?
Yeah, well, why don't you do that, and then we can get on to the questions. That'd be good.
Okay, so programming models. Why are we in the fix we're in? I feel as if we're in a fix right now with a profusion of programming models, and it's because of physics, of scaling laws, which we all know very well, between the feature size and the power. And so what we've done is build specialized widgets that do a smaller thing, but do it very well rather than a general purpose thing. And so that is a cause of a lot of problems. So that's one factor that is leading us to a lot of new ideas in programming models, this idea of specialization and putting heterogeneous pieces together. Another driver is algorithms, fundamentally new ways of approaching difficult problems. So we have extremely bright people, and for quantum, a breakthrough was Shor's algorithm that showed new ways of doing integer factorization using quantum bits and qubits and a quantum computer, and that really led to a surge of programming model ideas of how do you embody that, and how can you reason about it at a higher level of abstraction, which we've also touched on earlier. And the final is the convergence of technology and algorithms. So we've had multi-layer perceptrons for many decades, but the technology innovations to be able to collect and retain large amounts of data and process large amounts of data made those techniques dominant, so that now they're routine. Everybody has to mention deep learning at some point in whatever they're talking about. So how do we do it? As people have already said, we pull out the abstraction of the key capability of the underlying mathematical model or the underlying widget, whatever that device is that we're trying to use. So for example, for quantum, qubit, the complex plane, tensor, unitary matrices, Q0, the operations. You target programming models that are very high value, so GPU programming, abstraction of the hardware with a number of different languages that have emerged. Quantum, again, programming model is the abstraction of logic operations on quantum bits. And then neural networks, a profusion of programming frameworks, so models and languages to support very complex neural network topologies. What do all of these have in common? today, of course, is the parallelism. So it can be data-driven, it can be systolic, synchronous, it can be asynchronous, it can be task-driven, hierarchical, task-driven, combinations of all of those, but parallelism is a key driver. So what's the future? To me, the future is system-on-chip-like environment. So heterogeneous compute models, data and/or control-driven, tightly or loosely coupled. But it's if you work for Apple or worked on cell phones, that SoC environment. And I have a background in reconfigurable computing with FPGAs, and that is the combination of SoC-like environment and higher-level programming. So it's a difficult environment to work in, but I see that's where we're going. On the other side, I see workflows for programming model interfacing and mapping. So a lot of times you think of your best DSL, your favorite DSL, it's just so elegant and so mathematical, but it has to talk to other pieces of things, and how do you make it do that? How do you interoperate? And in the large and HPC and workflows have embodied some of those ideas of being able to interface and map. And then, as we've seen with other speakers before me, shared distributed heterogeneous memories, those are first-class citizens, and we often have to bring them up to the programming model level to be able to reason about them and use them just for performance. Ideally, everything would be uniform access. So what are the challenges? Well, portability. You've got all these different DSLs and languages. Depending on where you're going to run, the algorithms might be completely different. So you might want to have, and often you do have, multi-version implementations. Sometimes you want to be able to select them and adapt them at runtime. You want introspection. You've got a very complex, heterogeneous parallel machine that you're working on. You need to know what's going on inside, because that affects performance, it affects correctness, and so that's debuggability. And that we've seen some good from Torsten, a really nice way of being able to look at that. I've already mentioned interoperability, so we have multiple instances of the same thing, heterogeneous collections, hierarchical collections. How do they all work together? Right. How they.
Maya, you're cutting out.
Okay. Yeah, Maya seems to be cutting out. I can't hear her.
Yeah, I can't hear you either.
Okay. Well, in that case, while we wait for Maya to come back, why don't we move on to talking about some other questions? Maya, are you back?
I was never away, but apparently I was not coming through it at some point, and I'm sorry about that.
Yeah, I think we just missed the last 15 seconds or 20 seconds of what you were saying. So you were on that last.
Eureka moment, you guys.
That was the best part. All right, good. Well, now that you're back, I'll point out we're starting to have some questions in the Q&A, and let me just highlight here. Maybe we'll start with the first one, and I'll note that people can ask questions and also upvote questions that they would like to see addressed. So the first question here says, raising the level of abstraction improves productivity, hopefully portability, but reduces flexibility and customizability. And the audience member would like, Michael Wolf, I suppose, would like some comments on this. Would anyone like to comment on this trade-off between flexibility and level of abstraction?
I would love to talk about that because actually I had a slide that I didn't use that was
Okay,
that very
great.
point.
Then yes, please go ahead and start.
Okay, so a long, long time ago, probably sometime before some of you were born, I designed a language that was called Data Parallel Bit Serial C. And what it did is it took a processor in memory chip, an SRAM array with bit serial processors, and it abstracted that so that now you had a data parallel language, but your data types could be arbitrary length integers. If you had an integer, it could be arbitrary length, so you specified the length. And that was it. That was the data parallel language. Beautiful abstraction, a beautiful chip. Well, what happened? We developed the compiler. But what actually worked in practice, the way this chip was used, was for a very incredibly smart guy to get in there and write microcode. And he wrote microcode that enabled data paths that were hidden, that were not accessible within that abstraction to get the best possible performance on the sorts of algorithms he wanted to do. And I think that exactly addresses the question that you need to get under the covers sometimes, and that's why you do it, performance.
Well, can I add a little bit to that?
Torsten.
Okay, so actually, I agree and disagree. So if you just take the path that TensorFlow, PyTorch, and many of the deep learning frameworks have gone, namely to abstract operators, like this is what Onyx is about, this is what many of these frameworks is about, then we are limiting ourselves to one particular use case, to one particular domain, which is perfectly fine in the deep learning world, but maybe not so desirable in the high-performance computing world. This is why I'm concretely proposing to actually abstract the data movement and the data structures, because they're more versatile than specific operators. Like there are underlying patterns that are, think about trees. You can use trees for all kinds of different things. However, if you just say there's a specific function on a tree, then this is only this one function. Furthermore, if you go higher level and just think about the data flow, then it's even less specific than data structure. So you really need to adjust what you're doing, I think. And going just operations may be too specialized, in my view, for us as a community.
Okay, all right. Justin?
Yeah, one quick comment that I'd like to add to everything that the other panelists have said is, I think that whoever asked this question is right in some sense that if you are looking for a higher order programming language that is general purpose, you oftentimes run into these issues of getting outstanding performance because you're trying to cover potentially all domains at once. But I think if you work in higher order domain-specific languages, I think that many of the challenges that people have traditionally seen start to vanish. So for example, let's go back to Halide. That came out of Saman's lab, as I understand it. And what JRK, Jonathan Reagan Kelly, who's a professor now at MIT, has shown is that through Halide, you can have superhuman performance and you get portability across numerous heterogeneous hardware backends. And the reason for that is because it's domain specific, and we can then target different hardware with the semantics that are represented in that language. Now, I think if we are targeting general purpose languages and try to do this type of intentionality, it may result in what this question asker is presenting. But I think that with domain specific languages that are intentional by nature, I think this problem may start to manage itself.
So let me add. Sorry.
Okay. I think Kathy's next, and then Saman.
Okay, sure. Kathy, go ahead.
Great. Well, I just wanted to add one more thing on the data movement. I'm completely aligned with Torsten on the importance of optimizing for data movement, but also and this question about domain specific. I think that we should separate the question of what level at which people are writing applications and the level at which they're executing. And certainly we need compilers that actually understand that code well enough that they can, for example, turn something that looks like a bulk synchronous or almost kind of serial step-by-step kind of computation into something that is optimizing for load imbalance, optimizing for asynchrony, overlapping communication. But on the reducing communication, I would also like to think about what we're working on is looking at much more irregular data structures. So, to Torsten's point, not just looking at operators, but looking at the data structure. So how can you minimize the communication cost when you're doing something like constructing a hash table, or when you're looking things up in a hash table, or when you're walking over a graph or things like that. So anyway, I think that brings up a lot of other interesting questions. So far, it seems like domain-specific information is really important for being able to do some of those communication optimizations and those irregular sorts of problems.
Great. Sama?
So normally, if you're handwriting a high-performance piece of code, it has to interleave multiple concerns, so you need to get performance. What domain-specific languages try to, and compilers try to do, is separate them into different dimensions. So Justin just talked about what Halide does, separating algorithm language with scheduling language. So things like data movement, computation movement is separated. So you can do you can do different as you move, but hardware move with problem to problem. You can do different things. In recent language we did Taco, tensor algebra compiler, we even moved out the description of each tensor's formats to a different language. So you can have the same expression, you can have things like CSR or DCSR or a dense array, you can do that. So idea of a good domain-specific language is not to constrain your choices, but make it much more easier to express your choices. You are not putting this entire thing into one spaghetti ball of code that if you want to change something, you have to unravel this and put them back together. So I hope if we are successful, it will make it much better, easier, not harder.
Okay, great. Justin Notho has his hand up, so I'll call on him next. But before I do that, let me just point out we have two kind of follow-up questions in the Q&A, which are sort of similar in spirit. So one says, how do you avoid the fragmentation of having too many languages where each is too small to individually gain traction? There are a lot of proposals, but most code still uses older languages. And there's a second follow-up as well that says, how do you address Maya's comment about longevity? Who maintains these DSLs over 10 or 20 years? Okay, so I just want to inject that into the conversation. Justin?
Super. So I won't try to answer those in too much detail, but I may just sort of tease out some high-level ideas. The reason why I raised my hand is I wanted to go back to Torsten's and Kathy's comment about data movement. Being at Intel for over a decade, when I joined back in 2010, Intel was very much a monolithic computing company. It was just the CPU. And as I suspect everyone in the audience knows, that we now consider ourselves to be very heterogeneous. And one of the core challenges that we see today is not so much in the compute, but in the data movement. So I just wanted to quickly acknowledge that I think the data movement and figuring out how to deal with that, especially as we grow into more deeper stochastic systems that tend to improve in their accuracy as you have more IID data, so independent and identically distributed data, that it becomes even more important that we figure out how to handle that data movement problem. So then as far as those two questions go, I think that this idea of fragmentation across DSLs, one idea is that there's this new field emerging, and I suspect lots of people are aware of, transpilation, right? So it's fundamentally different than compilation in the sense that you're not just lowering to a specific hardware architecture, you're taking an implementation of something from one programming language and moving it to a semantically equivalent representation in another programming language. And there's actually a number of success stories, Halide through the Adobe Photoshop example is one, where it started in C and C++ and then automatically transpiled through a formal verifier that the semantics were captured in the new implementation. So I think that that's one way to potentially deal with that. And then I think that slightly teases out a potential answer on how to deal with things like Maya's language that she created decades ago. How can we take the programs that exist in that language that are likely very useful, but have maybe 5 programmers in the world today, and move it into a DSL that's emerging, that is, has much more software engineering support? I think transpilation might be one possible route for that. So I'll give way to the other panelists now.
Okay, Torsten?
So yeah, I want to do 3 things. I want to first reiterate what Kathy and I have said in with different words. Really, we need to separate DSLs and optimization. So a DSL should not be a vehicle for optimization. A DSL should be a language that is optimized for the domain at hand and should enable efficient compilation or transpilation or whatever you want to call it to some other language that is then made for optimization. In fact, we've been doing this in compilers with internal representations for decades. Somehow this got forgotten in many DSL implementations that I've seen. So, for example, if you had a climate DSL, that should be good for the climate scientists to express stencil calculations and debug stencil calculations and be highly productive for that scientist. And then you could translate this to some kind of internal representation that is data movement centric. And this is exactly what we are doing with our DAYS project that I just showed you. We have these graphs, these parametric graphs, that is our internal representation. And the domain scientist the performance engineer does not understand the domain scientist at all. The performance engineer just looks at the data movement and is an expert in optimizing data movement. You cannot be an expert in everything. So it's very unlikely that your performance engineer understands climate science. And then it is decoupled what these 2 things do. And now the big question is, the 2 other questions, I love these questions, fragmentation and maintenance. I would just shorten them. And I think we should do exactly what Python did. We don't address those questions. We make it extremely simple to write DSLs in a very productive way. So think about Python. Python has been designed as an ecosystem to write libraries. So there are a gazillion libraries, Python libraries. 99% of those are not used and not useful. But the ones that win, they win big time. And they're maintained by a community. So why would we not just adopt that mechanism? Don't call it libraries, but call it domain-specific languages. So what we now need is a language that makes it trivial or extremely simple to write new DSLs so that everybody can write DSLs. So I want to write 5 DSLs a day. And that then emits some kind of internal representation that the performance engineer can deal with. And that, of course, that needs to be standardized in some kind of interface like a compiler IR, like the LLVM IR. But we found that the LLVM IR is not particularly suited for data-centric optimizations because of pointers, which is just deadly in there. But we have an internal representation that is suited for this. These parametric graphs, they work actually quite nice. So why don't we do this? And just ignore all of those. Let the community decide.
Okay, great. We may come back to this theme, but let's also pick up on another thread that we've been talking about on data movement. And the next question says, does data movement, the data movement paradigms that we've been discussing still hold for memory chips such as the Precipice or IBM Loihi or other new paradigms for computing chips? How does that affect the way we view data movement in this context?
I would like to, for some reason I can't raise a hand in that participant, but, so let me get my comment in now and then I will
Go ahead.
raise my hand. So I would encourage whoever put that question in to look for a paper by Camille Rocki, R-O-C-K-I, about Cerebras. And while there's a beautiful, whatever it is, TensorFlow or PyTorch or whatever, framework for the wafer-scale computer, he was doing an HPC algorithm, and if you go look at that paper and look at some of the code and the pictures in there showing the data movement that is so critical of each core passing messages to adjacent cores and how the neighborhood was laid out. Data movement was absolutely critical in that particular algorithm. And I think yes, it's present in all the chips.
Justin?
Yeah, just two quick comments. One is actually back to Torsten. I really like the way that you articulated the DSL comment, and I apologize if I miscommunicated, because the way you articulated is the way that I sort of envisioned it in the future, is really the DSLs are meant as a vehicle of separation of concerns. And I think the point you made about the expert in weather versus someone that is a ninja that really deeply understands systems, it's super unlikely there's an intersection where this one person exists. And so I just want to reinforce that I think the way you articulated that, I think is dead on and is exactly how I think about it. And I also really liked your programming language framework for DSLs. I haven't thought about that much, but now that you mentioned it, I think I'm going to think on that more deeply.
Thanks.
So thanks for sharing that. The one comment I wanted to quickly make was about Lohihi. So I work very closely with Mike Davies, who runs the neuromorphic computing lab out of Intel Labs. And part of what Mike and I are trying to do with neuromorphic computing is figure out what the programming models look like for those systems. So what I can tell you is, at least from my purview in talking with Mike, is we don't exactly know how to deal with the data movement issue. It likely is going to be very important. There's also larger questions about programmability. I think similar things are raised about quantum, but I think that it's important for us as a community to maybe, instead of trying to jump right to the answers, continue to try to find the right questions to ask. And then once we can figure those out, we might start to be able to formulate how we can actually start to address those questions. So yeah, that's all I want to share.
Great. Kathy?
Yeah, I just wanted to make a quick point on that, I think along the same lines, which is, I think each of these new types of architectures change the balance, and they change the place where the communication, the data movement can be most expensive, but it doesn't really make the problem go away. It just means that, the question of how much memory do you have locally, very close to a compute unit of some kind, and how much do you have that is further away, and especially if you want to solve a large problem, whether it's a large simulation problem or a large data analytics or machine learning problem, you're going to have different places, which is why I think we want to think about hierarchical algorithms and programming models that allow us to express them, and so that we're not programming to a particular machine with a particular characteristic, but anyway, trying to make sure that I think we're going to have to worry about data movement regardless.
Okay, great. So let's sort of move to next question that is thematically related, and this one it's tagged for Torsten. It says, is or can data movement be expressed entirely in an architecturally agnostic manner? Same for cache locality, network bandwidth, so on.
Yes and no. So it depends on exactly what you mean. The nice thing is, in theory, each application or each execution of an application can be modeled as what I would call an execution DAG. Right? Each operation is a vertex, each data movement between, or each dependency between operations is an edge. So you can, independently of the target architecture, like we were teaching in parallel programming, I'm teaching this in the second semester. So independently of the architecture you're executing on, you can describe the data movement, the work and the depth of an application theoretically, right? And this is what we capture in these parametric graphs that I was talking about. So these are simply graphs that, for so-called data oblivious applications, capture this in an O of 1 representation, essentially. What Katie was talking about, the more irregular applications, they're much harder to capture. So these we don't teach in the second semester, but the other ones are relatively simple. However, now as you start going down, as you start optimizing for a particular target architecture, of course, you need to take into account the sizes of this architecture, like what Kitty was saying, the sizes of the memories that are close to the execution units, the exact tiling constants, and all of that stuff that needs to be taken into account. But what we do in our representation is we start from the application representation, which is fully independent of the target architecture, and then we go through multiple steps of lowering, so you could think MLIR here in more and more specialization to the target architecture, where we apply what we call transformations that change the graph from one representation into another semantically equivalent representation, but that is better I/O optimized for the target architecture. So yes and no is the answer. You can describe it completely independently. However, if you want to execute it fast, you better get your target architecture into the picture. So one last thing I want to say is that this is extremely cool if you think about different architectures. So if you think about GPUs, CPUs, and FPGAs, all of those have fundamentally different ways to move data. So CPUs are these latency critical devices where you can actually have random access and it works quite well. GPUs is a bit more complicated because you now need to worry about bank conflicts and all of that stuff. FPGAs are completely crazy because you have to lay out everything as a pipeline essentially, otherwise it's super slow. So these are very different target data movement constraints you have in order to have your application perform fast on that device.
Saman?
So it's very interesting to talk about this because 10 years ago, when there was a real push to teach parallelism for our students, we made the decision, before we got parallelism, we had to talk about performance engineering. So parallelism doesn't talk anything about data movement. So performance engineering about caches, about data structures, all those things that are necessary. And the current undergraduates who just learn Python has no idea how any of these things work. So instead of trying to do just parallel programming class, we just started with the fundamentals of performance engineering there. So in some sense, you need to build that up. I will add one more thing interesting. So we talk a lot about libraries and we talk a lot about DSL. So what's the difference in there? There's one big difference in my mind. Libraries can be a kitchen sink. If you want something to keep adding to that, you can keep growing like crazy. Compilers, unfortunately, you can't do something like that. What compilers has to do is take a big problem and to see that you can build out of very few foundational units. And then the combinatorial explosion of those foundational units will give you this expansiveness. But you can't independently say, I'm adding this, I'm adding this, I'm adding this. Any language that try to do that is not that much of a successful language. So in some sense, I think the hardest part to convert a library into a DSL is to say, okay, this library has 500 different functions in there. Are there 3 concepts that can be used to build all those 500 mostly? If you can identify those 3 concepts and then little bit of variations after that, that is how we can build a building. So that is why I think DSLs are harder than libraries because and then when you move out of that concept, I can't just keep adding more functionality. I said, okay, I ran out of my bounds of this DSL. Okay, now I do something else.
Maya?
So I wanted to go back a little bit to the data movement topic. And what I wanted to say is that here, I believe it is absolutely critical to have visibility, to actually be able to see in some way what data movement is going on. And I want to give an example of, I don't know, 10 years ago, some of you might remember the Ambric chip Mike Butts and his group developed. And that had this process model, beautiful model, Java-based language, a nice simulator, just an incredibly wonderful programming environment. And it was all based on FIFO's installing. I mean, that's what the hardware was doing for you. The problem was that if your pipeline wasn't balanced, you would get these stalls, and you would see, like peristaltic motion, you would see the stall going out and then bouncing back and forth and back and forth. And so what you ended up having to do was balance, manually go in there and balance your your compute unit so that they were producing at roughly the same rate. But to get that insight, you needed to see those stalls and see it actually happen. And I think that is so important in either through simulation or some sort of analysis to be able to actually see what data movement is going on.
Yep.
Great. Torsten?
Yeah, so since we're on a panel, I found the first opportunity to actually disagree with somebody. So Saman, I'm going to disagree with you. So let me repeat your statement, and you're far away, so, well, I'm winning. So let me repeat your statement that it's harder to write DSLs than libraries. I don't think that's fundamental. I think this is what we do today, but if you think about it, going from a library to a DSL, both of them implement some functionality. So I claim I can take any language and I can implement it as a set of library calls like many do in Python. You just have to use the predefined syntax. And as proof, I would give you template metaprogramming, where you use your predefined syntax, and I can basically write a compiler in the template metaprogram, and I can use Python, these wonderful decorators, to do something very similar. So now this boundary between what is a library and what is a language is actually getting extremely fuzzy, at least in my head. So for the sake of debate, could you try to disprove me and tell me what the boundary, where do we draw the line between the library and the compiler, and what do you really mean by this? Because I think it's not fundamental. I think we can do it with the right technique.
So let me, so yes, you can basically, library can be considered a DSL. You can do some very simple things and get a DSL.
And the other way, I think.
Most of the time, when you try to do a DSL, it's to get something more deeper. We want to get something much more comprehensive in there and much more deep into that domain. So if you look at something like, we'll say, tensor algebra, when you get a linear algebra or tensor algebra library, there are thousands of functions, each individually done, separately done very well. But then if you want to build a compiler for tensor algebra, I can't say, okay, I need these 100 functions to do that. I need to really think what is fundamental about this.
I can. This is what we are doing.
Yes, but it's harder than doing libraries, because libraries I can just keep adding something. It doesn't have that much dependence to anything else. If I can use the data structure in there. Whereas if you build a system with some core principles, and then using that, if you have something else that outside the previous, yeah, you can add it to the side, it will live there, but that's not doing honest service for that part. So that doesn't fit into your model in there. So part of that is why I think a good DSL has to be thought through carefully, and also it's not infinitely expandable. Whereas I think libraries can keep adding and growing and adding things into library easier.
So you must hate NumPy.
Yeah, exactly. NumPy is a very good example of that. You just got to basically, you just can't. No, it's a good library. Library can get expanded, but convert number like NumPy into DSL, true DSL, might require actually multiple DSLs because there are too many concepts in there.
Okay.
Kathy?
All right, so this is my standard spiel on, why a language rather than a library. So I think there's three things we should separate. One is I think what we're talking about is, do you have a compiler, or do you just, a compiler for that, say, DSL, or is it just embedded in, is it a library embedded in some existing language in which the compiler doesn't have any specific knowledge of that library? But I think that the difference is, can you get special syntax? And I think most of us would say syntax isn't important from kind of a programming language standpoint, but I have to say from a user standpoint, I think syntax does matter. And people do care about some of that higher level syntax and some things that look familiar to them. I think the second thing is, do you get any kind of semantic checking from it? And in a library, typically, if you miscall a library routine, nobody tells you about it, unless the types don't match or something like that. But you really, in something with a higher level language and compiler, you can get a lot more semantic information back. And of course, you can get optimizations and higher performance across the different routines, whereas in a library, each one is optimized. It's really, I realize you can build libraries in which, the routines don't actually run at the point you call them. They all sort of of get accumulated, and then you run some compiler-like thing that makes it run faster. But for the most part, I think those are those would be, I think, what I would say are the differences, and I think the advantages of having an actual compiler. And I think finally, there's a tremendous fear of compilers out there. Like, oh, we can manage to maintain any complicated library you could build, but don't make me maintain a compiler. I mean, this is ridiculous. It's another piece of software. We just need to train some more people who understand compilers, which is, I think everybody here on this panel would be very happy to.
Yeah. Actually, what Kathy just said, last thing is in fact a compiler. The library puts all those things together then and massage. That's basically nothing but a compiler under a different name.
Justin?
And Python decorators you can essentially use to implement your compiler of a language. I mean, that's of a library calls. That's what we're doing, right? So you just parse whatever has been passed to the thing, and you understand, of course, the semantics of your NumPy calls, and then you can see NumPy as a language. And you can actually also design semantic checkers for it if you want to. I'm not saying you want to because it's not designed to be done, but you could.
So, in fact, one project we have is this language called Cola, C Cola, basically where we take Python and do static type checking of Python, exactly. and basically compile the hell out of Python. So all these things I can optimize in there, and NumPy is a good example because instead of having these separate NumPy calls, I know exactly the control flow and I can merge these things, do a lot of cool things.
But that's the thing. I mean, we need to accept that it's that way, and we need to take the next step, because right now it's a bit of a mess if you think about it. So we have all these properties that Kathy is telling that languages have this, but we need something new that we can really productively design these new languages. Right? And Python is not really it, I agree, because it's written for libraries, but now what is the next step and how do we take it? Sorry, Justin, now I let you.
Oh, no, by all means. This is a great debate. Hal, can I just share one quick slide since it's, I think, highly relevant to this discussion. And this is sort of inspired by Kathy's comment that I want to just quickly discuss. So at Intel, obviously, we do quite a bit with compilers and things. I'm just trying to move this out of the way. I don't know if this is blocking anyone's view. But so this is sort of inspired by a number of work that I've seen lately, but we can go back to the verified lifting Halide example. I think fundamentally the way that we've done compilers, especially if we want to embrace heterogeneous hardware targets, I think it's fundamentally flawed. And I can say at Intel, we're having a heck of a time keeping up with the heterogeneity, simply for the reasons that we all just discussed, is we don't have enough compiler engineers. So how do we overcome this? One of the ways is, I think, that we try to invert the problem. So rather than having ninjas, we instead try to lift out the higher order semantics into some DSL that's probably very succinct and probably in some sort of lambda calculus formation. So it's compressed, but it's still Turing complete. And then after the semantics have been lifted, then the beauty of this is it allows us to do things like automatic parallelism, where we can do full algorithmic rewrite. So you can take something that's implemented in like O of n squared complexity, lift out the semantics, understand, oh, this is a sort. Wow, I can rewrite this sort using quicksort, and now suddenly I can get n log n optimization. But if we are driven by syntax alone, we know that the syntax tends to not capture those higher order semantics, so it doesn't allow us the ability to do full algorithmic rewrites. So my view of the future, and this is actually a technical strategic direction, a TSD at Intel, for future development of compilers, is to essentially start to invert this, not do this type of thing. And I'm not saying that syntax doesn't matter. So Kathy, I fully agree that syntax certainly matters. Especially when you start to bind the semantic meaning to a lower level syntax. So that's critical. But just one higher order point that I wanted to quickly talk about. This is how I think about compilers in the future. And I think this is one way we can potentially get over the lack of ninjas that we currently have. And then the other comment I just wanted to quickly make is, Torsten, I agree with Saman, actually. So I fully respect the point that you're making, but I think if I understand Saman correctly, what he's trying to get across is that it's not that you can't do this with libraries. You can. It's just significantly harder to control. in that if I write a compiler that is forcing a limited grammar for a DSL representation, I can ensure that that doesn't get expanded on. But if I write a library, any programmer can come in and just toss something else into that library pretty easily. And now I have everything in the kitchen sink, and suddenly my ability to optimize across something that was supposed to be domain specific suddenly becomes generalized. And now I lose the ability that I was originally shooting for. So just my high level thoughts on that.
Sure, but we are not there in production. I mean, you started with the deep learning stuff, right? None of those are, most of the ones that we're using are libraries. TensorFlow,
oh,
PyTorch,
so yeah, so this example that I just showed with verified lifting and Halide, that's in production quality code today. If you download Adobe Photoshop version 21, that's actually, you'll download the Halide optimizer to do this very thing. So it is actually in production.
Sure, but I was talking about deep learning. TensorFlow.
Oh yeah. So Halide, their autotuner is a deep learning system. Mm-hmm. It uses a deep tree convolution search.
If I was to implement a deep learning network, like a transformer, I would not be using Halide today.
Oh, so I guess
you'll use something like TVM that also has a very similar.
Oh, I see. Yeah. Okay. Yeah. I think I see what you're saying, and yeah, I might say use TVM as well, but I'll stop talking now.
Okay, yeah, so we have about 25 minutes left, and I just want to kind of preface the themes that are left here in the Q&A. So there are three I want to point out. So one is there are a couple questions here about data movement, whether it's the responsibility of the hardware or the language, and whether it's implicit or explicit. That's one theme. Second theme I want to point out is there's a question about compiled languages versus interpreted languages. Like, is there room for new compiled languages, or are we going to focus more on interpreted languages? And the third thing I want to point out is about heterogeneity. Because the question says, computing is becoming available everywhere, DPUs and smart NICs and smart SSDs, and how does the future HPC programming models take advantage of those? So. And I really just want to make sure that we kind of get across what everyone's vision is for how programming an HPC system is really going to be different in the future, and so we can try and address these things. So why don't we'll start and work through these different themes. Why don't we just pick up on maybe a point that just came up about languages and the fact that maybe you download the Halide optimizer. So comments on are we looking for or do we see a space for novel compiled languages, or are interpreted languages or just-in-time compiled languages the future in this context?
So one thing I would say is this is getting very blurry. So for example, we have this system where we are compiling Python, and we can do compiling, and Halide and stuff like that has compiling built into the runtime in there. So it's a just-in-time compiler part of that. And what I see is with cloud support, right now this compiler is supposed to be very long-running processes that run for a very long time, and you can really reduce it. So right now, if you do NLP, you don't do NLP in your smart device or computer. You put it back to the cloud, do huge amount of work and get things back. We can go in the direction of compile. When compilers start doing that, the compile time will go down because compilers is inherently very parallel. You do a lot of things in there. And so if I have a cloud compiler, I will be able to separate the distinction between compile time, runtime, just in time, because this will come down in here. So in the future, I don't see this huge differentiation in there. But I think as things like data movement become very important, compilation comes, because in some sense, one thing compiler does is it look at the global flow of things. Well, that's something fundamentally library can't do. Global flow means data movement. And if you have that global vision of data movement, I can make sure that I don't basically do one thing in another and then completely rearrange everything, go to the next part. I can put them together in a coherent fashion. So I think that will be important. However, this thing about explicit versus implicit data movement, that question I would say is, one thing Halide showed is you can separate concerns. You don't have to embed everything into your algorithm part in there. So algorithm can be pure, simple, and then you can do additional information, things like data movement around it. So if you really want to get good performance, if you really have some crazy system in there, I will be able to augment my program to get that in there. So let me add those 3 endpoints and stop there.
Great. Maya?
So going to the question of compiled versus interpreted. So we thought there was room for another compiled language, and then I see everybody wants to do Rust. That's, you know, whatever you can write, you've got to, whatever new you're going to do, you've got to do it in Rust. That's the new compiled language. From my viewpoint, having used compiled languages and right now doing a lot in C++ and not enjoying it at all, I would have to say that I love interpreted languages. I love instant feedback. So even with my C++ compiled language, I really like making one small change, seeing that change immediately within seconds, being able to test it, and then go and do the next thing. And that's the essence of interpreted languages. That's productivity. And having worked with, again, with FPGAs, and that extremely long, oh my God, I've got to go through another synthesis place and route, well, I might as well go work on a different project for the day. So, you know, I'm torn, and I see a dichotomy, and there's a place for both when you really care about correctness. And I mean, Rust tries to enforce all of those things, and safety and all of those. Maybe it's worth the pain to do that, but I must say I really prefer the quick turnaround and the interpreted flow.
Justin?
I'm going to act more as an echo chamber, I think, here for Maya. As some of you may know, I created my first startup when I was 25. I'm 47 now, and I wrote about 500,000 lines in C++. So I'm pretty well versed in that programming language. And as Maya pointed out, it can be really painful to observe changes because it's slow and it does so much static level analysis and type checking and that type of thing. But on the other hand, I took what I would call my sabbatical at Intel, and I worked at a startup where I programmed principally in the programming language Lua, which is fully interpreted. And Lua is a beautiful language. I was able to do a ton of things really fast. But one of the points I think that Maya said is I sort of see it as a dichotomy, is that on one hand, these interpreted languages are great for productivity, but also sometimes they can be really scary. That I almost think that you need to be a better programmer to program correctly with the interpreted languages, because there's so much abstraction that oftentimes if you get something wrong, you don't see it immediately. And we had many cases where we released our code and we thought that it was fully tested. We thought we had the coverage. It turns out that we didn't have the right sort of like interference from multiple threads, and we weren't able to get that type of behavior teased out. And then suddenly we run into these crazy bugs that maybe it would be caught in a compiled language, maybe it wouldn't be, but I think there's certainly this, there's tension, I think, between those two. So I have no answer. I more just agree with Maya.
Okay, Thorsten?
So I'm still young, naive, and greedy, so I'm going to disagree somehow. Trying to a panel here, I need to discuss. So I think we can do both. And I think I have proof that we can do both. So what we do is we have a climate DSL that actually runs a significant climate code. We can run this on Python. It's a Python DSL. We can run this in interpreted mode and have rapid development, so programmers can type stuff immediately, see what's going on. So Maya is going to be happy. But Maya is also going to be happy to hear that we can click a button, and then 2 days later we will have an FPGA image. I'm not kidding with the 2 days, it actually takes 2 days. Which is quite sad for these tool chains. Xilinx, please get your act together and do something. But anyway, so Intel as well. So I think that's what we should aim for. We should aim for rapid development in an interpreted environment, because that is what I want as a programmer. But as a performance engineer, and to get the latest, greatest performance, I do need heavy static analysis. I do need place and route, even on future devices, programmable devices like Cerebras. They also have a place and route, essentially, if you don't do it manually. So we need both, I think. The only problem that I see with this whole approach is that if you're a performance engineer, then you're in hell. Because now you care about the performance, not about the functionality. Domain scientist, happy, interpreted. Performance engineer, oh my God, now I need to tune that system somehow and measure the performance. But otherwise, at least the domain scientist can be happy. So now disagree.
So Thorsten, I would just have to interject there that it is not push a button and get your answer out 2 days later. You might get something out 2 days later, but it's 50-50 if it's your answer between critical paths, bugs in the tools, and all the other things you encounter.
Well, have you tried our thing?
I mean, I have been talking to many companies. Part of a success for a company for me is they have to rewrite the entire software, because they wrote it for working for 100 people. Now there are 100,000 people using it, and suddenly it become way too slow. So somebody like Facebook rewrote the compiler and then tried to get the program running fast. And a lot of other people, basically a lot of software engineering is to go clean up something that was written for 100 people. Now it's 100,000 people. So there's a lot of Python code rewritten in C++ because they were very successful Python code.
Yeah, Python is not a language for large-scale software development, I think. I was never designed to be, but people do it. Agreed.
All right, so let's move on. We have a question here about heterogeneous computing, about DPUs and smart NICs and smart SSDs and all these things that are appearing in the HPC landscape. And how are HPC programming models really going to adjust for these? We might fold in this question about implicit versus explicit data movement in this context as well. So how will HPC programming models evolve in order to capture these new kinds of places where computing can happen? Maya?
So I would have to say with something like the smart SSD or smart NICs or those sorts of edge and more distributed sort of computing, that message passing is your friend. And yes, that it would be nice to have the shared memory and the threads and all of that. But what I've seen is that the message passing is really what works well, especially if you have to transform data types in transit from one modality to another. So that's how the workflows and that sort of thing. That's why I put that section on workflows into my overview, is that I really think that's where it fits.
Summer?
So again, interesting thing about HPC is every time a new architecture comes, you have to rewrite the entire piece of code. It was vectorized, it was distributed memory, it's shared memory. And the nice thing about DSL is if you do it right, you write the algorithm once, and if the algorithm don't change, you don't have to change that. So if there's a new modality come about that needs different type of explicit communication, yeah, you can do it in the side, the way Halide does. So if you get that right, then the algorithm part will stay consistent. So you don't have to go and really reprove that your code is actually solving the same problem. So I think we have a possibly for the first time have an opportunity to basically break that cycle, that every time a new machine comes, you rewrite the entire high-performance application suite. Yes, you might have to rewrite the optimization part. Somebody might try to go tune it, but I don't have to go find my domain scientist and say, please, I had to redo everything. Did I do it right? If I do it right, I will be able to map that in there. And because I get that specification right, like what we are finding in things like Halide, now we might be able to use some automated techniques to kind of tune it to a given machine. So my hope is going to higher level abstractions, that I will be able to rapidly adapt to a lot of the technologies coming by without really forcing that up all the way the tool chain to the domain scientists.
Kathy?
So I agree on the not forcing it up the tool chain to the domain scientist. I think that I would maybe I'll try to be controversial here and disagree with Maya and say, if by message passing you mean two-sided or collective, I think that may not be the right mechanism for a lot of the data movement that has to happen. And I think there are places in the software stack where you're going to need to make data movement explicit, not just implicit, maybe not at the level of the domain scientist, but I think when you're optimizing for communication, you do want to use things like DMA mechanisms and decouple the synchronization of data transfer from the data movement. And so I think that, I guess in terms of what is explicit and what is implicit, I think it depends a lot on the constants, like what are the costs of things, and that when the data movement becomes very expensive, you probably want to manage it directly, explicitly. And if it's something that is when the cost is lower, I mean, this is the difference between having a cache and a shared memory system and having a distributed memory system where you're talking about, the difference between nanoseconds and microseconds of delay. Then, you really, probably have to go to something where you're certainly explicitly laying out the data structures, and you're also, if you're not explicitly inserting the data movement, at least it's fairly clear from the higher level application, and so the compiler is putting in the data movement at the software level.
Kathy, I agree with you. What I meant by message in a generic sense was like a mailbox. So you press go on a configuration register and then the DMA goes.
I should have known that, knowing you, Maya, that you were talking about that.
Okay, great. So we have about 10 minutes left. So let me see if I can go around in our last bit of time and get everyone to kind of paint a little picture. So let's just say 10 years from now, I sit down to write something for an HPC system. What are the two biggest differences that are going to face me then in that task compared to the way I would do it today? So Justin, let me start with you.
Oh, wonderful. Thank you for picking me first, so I have the least amount of time to think about this. Okay, so first and foremost, I'm probably going to be completely wrong, so I reserve the right to change my mind tomorrow. But I have thought a little bit about this, and I do work with some of the HPC folks, obviously, being in Pradeep's Pradeep-based super lab. I work with a ton of ninjas, and I also work with the math kernel library team, 1DNN, and so people that are writing like really fast code. The first thing that I think is likely to happen, and I'll probably get a lot of pushback on this, especially from sort of the hardcore HPC folks, is I think that because of the explosion of heterogeneity, specifically hardware heterogeneity, there's also, programming language heterogeneity, but just focusing on the hardware portion, in order for it to maintain like computationally tractable for us to sort of find reasonable optimizations across all of those heterogeneous pieces of hardware, I think that we need to raise the level of abstraction for representations of code, and that means being more intentional by nature. So the core idea is really strong separation of concerns and more intentional programming languages like Halide. Another example that I'd like to give is SQL. So SQL obviously is a declarative language, but if you look at the work that like Ryan Marcus and Tim Kraska and others are doing, they're getting these incredible performance speed up over what are literally like tens to hundreds of human years of development for databases, because the language is almost intentional, because it doesn't expose the lower level details. And then if you look at Ryan Marcus's battle paper that just won the best paper award at Sigmod this year, you'll see that it's largely because of that abstraction that he's able to get this incredible performance. Now, whether or not that will apply directly to more deep scientific spaces in HPC, it's not entirely clear to me, but I personally think that that's going to be one of the core directions. So I guess that would be the first piece. And then the second piece is, because of all this heterogeneity, I think as everyone has noted, it seems as though we have, in some ways, we're very aware of the different needs of different compute. And so that's why we have a lot of different hardware computing devices coming out for different problems. But one of the open challenges I see is around data. And I think that it's only going to get worse as we build more deep neural networks or deep learning systems or systems that rely more on IID data. And so then the question becomes, how do we handle that much data? Is it a problem of compressing the data? Is it a problem of distributing the data such that if you're building this massive IoT system that's also with the cloud, the IoT system does some of the management of data and then somehow is able to send only a small amount to the cloud? All of these questions are unclear to me. And they also open up a bunch of privacy concerns. So there's a bunch of questions around ethics based on how you deal with that data. So I do think that that's still an HPC problem, because once that data eventually hits that cloud, then suddenly there's this mass amount of like continuous learning or something that's probably not going to happen too much on the low-end compute device, like the thermal sensor that you have in your house. But maybe when you send it up to the Google Cloud, then it's going to become an HPC problem. So that part, I think, is the second thing that is largely going to change in the next 10 years. Those would be my two things.
Okay, great. Maya, what do you think the most important two things that are going to change are going to be?
I think it's going to be the presence of heterogeneity within the supercomputer, a great magnitude of rise in heterogeneity. We're used to homogeneous clusters, large clusters, and that's going to change. And so you're going to have to be able to express the sorts of devices you want parts of your code to run on and reason about them. And the second is adaptation. So looking at the data and having the data help you decide what to do next. So I see those as the two. I mean, I see other, you asked for two.
Yes, great, thank you. Torsten, what do you think the most important two things are going to be?
I'm going to say something controversial, of course. So I think we will worry about the structure of the computation, so data movement as a performance engineer, and we will worry about the productivity as a domain scientist. The question is, how do we combine the two? Because they are fundamentally against each other. If you have to worry about the structure, then you cannot be productive. It's super complicated. But that's what we will do, I think.
Okay, great. Simon, what do you think the two most important changes of how we program HPC systems are going to be?
20 years ago, if you asked what is required to get performance engineering, you had to write assembly code. Today, when you are talking about high performance, nobody's talking about assembly code. We are at a higher level of abstraction. And that's because there was too much of different assembly code showing up. There was no way you could keep up, even today, you can probably get a little bit better performance looking at the vector units people are doing. As we get into more and more heterogeneity, you have no choice but to go up. And what I would say is, when I was doing compile optimization, like automatic parallelization of general purpose code, 90% of my work was to undo what programmers thought was a good optimization, to get back to the basics, because now I had to do something different. So something really nice that now I'm working on domain-specific languages, higher level is I don't have to do that. I only go one direction. I'm not trying to look for some crazy thing somebody did. They thought this was really good to do some register location by hand or something. Undo that everything, because instead of 8 registers, now we have a lot more, and you can get a lot better performance in there. So I think we are going to move higher and higher. That's the only way we should be able to survive. And if we don't go there, I think this problem is going to persist a lot longer.
Great. Kathy?
So I think the first thing, which is related to an earlier discussion, is that we're going to see a change in the balance of the cost of communication and the size of memories and things like that. Not that communication will become unimportant, but that the way you optimize, if you have very tiny chiplets or other sort of customized devices, and those are communicating explicitly, and you need to manage that communication between them, I think that's going to change the way we think about, much finer grained parallelism and things like that with explicit data movement. And I guess I hope that we will also be able to build higher level programming abstractions, and that most people, most domain scientists will be programming at that level, but that underneath the hood, through the combination of, fast libraries and fast translators, compilers, whatever you want to call them, will be actually able to execute on these. I don't think the systems are going to be heterogeneous sort of within, I don't think we're going to build HPC systems that have a third of this kind of accelerator and a third of that kind of accelerator, because I don't see sort of what the argument for that. I think clouds will look that way, because at a cloud platform level, you have enough diversity in the workload that you can sort of afford to have a whole bunch of different kinds of things, and whether you'll be able to tie them together into an HPC-like system is I think going to be an interesting sort of business question. But I think that I think that we will hopefully be programming at a much higher level of abstraction and dealing with all of these issues such as communication, memory size, balance issues in the underlying libraries and compilers.
Okay, and with that, we've reached the top of the hour, and I would like to thank all of the panelists. We'll have our virtual round of applause here, and I would like to thank the audience for joining us, for asking questions, and of course we'll hope to continue this kind of discussion in the future. So with that, thank you.
Thanks, Hal.
Thank you, Hal.
Thanks, Hal.
Bye.